Good evening and welcome to this 18th session of Astro Adda. Um, Public Outreach Committee, Astronomical Society of India, and Nehru Planetarium, Nehru Memorial Museum and Library. We welcome you to this Astro Adda session. Today we are going to be talking about inspiraling in spiral galaxies. So, for to take us through this spiraling in process, we have with us Dr. Mamta Gulati from the Thapar Institute of Engineering and Technology, Patiala, and whose work has been looking at galactic dynamics and who is going to take us through this parallel process. Is there a sound disturbance? Now, yeah. So, Mamta ji, I will hand over to you and you will be needing your presentation too. So, I will add it into the view now.
Yeah, okay.
And thank you so much for offering to take us through this process. I'll hand over
Yeah,
to you.
yeah. Thank you. Thank you so much, Ratnashri. It's a pleasure being part of the session. And I will be mostly talking about the inspiraling in the spiral galaxies, little bit of history and the history and the formation of spiral galaxies to be precise. Myself, Dr. Mamta Gulati, I'm currently working at the School of Mathematics at TIET Patiala. So let's start with the discussion. And these are the 5 pointers that uh, we'll be basically talking about today in today's discussion. So we'll start with the observational history of Milky Way. Then we'll move on to the classification of the galaxies and formation of the galaxies. Then little bit about spiral galaxies, a brief introduction, and the formation of spiral arms. Though I have added all these 5 pointers in the discussion, I may not be able to go in gory details of each of the pointers, but I'll try to give the gist of all of these in the discussion today. So let's start with what are galaxies. So galaxies are huge collection of gas, dust, and billions of stars and their solar systems. So I'm talking about, and they basically are uh, bound by self gravity of its components. And it's thought that there is a supermassive black hole at the center of most of the galaxies by now. And our own galaxy is called the Milky Way. And if you look at the sky and you're away from the lights, city lights, and there's no other obscuration due to clouds or anything, you can see a wide band that stretches across the sky like this. This picture is taken from Chile, and this is basically one of the spiral arms of our own galaxy, that is Milky Way. We'll come to these spiral structures and details of how Milky Way's shape was actually deduced in history. So the next we'll start now with the observational history of Milky Way. First, to start with, there are, other than Milky Way, there are many other names given to the galaxies, such as Akash Ganga, Celestial River, Galaxy Cuclos, and the Milky Way, which also mean Via Lactea in the ancient terms. And the first, I'll not go into the mythological context of the galaxy's mm, formation or galaxy's observation, but we'll start with the Galileo's first pointing of the telescope towards the Milky Way that happened in 1610, and he resolved various stars and deduced that the galaxies are actually stellar systems rather than fluid or anything else. And then it moved on in 1750. There was a lot of work that was done in between 1610 and 1750 to deduce the distance of the stellar systems to observe various stars. However, the next breakthrough which happened was in 1750, which was by Thomas Wright, and he gave a speculation that the galaxy might be a rotating object, rotating body with the large number of stars held together by its own gravitational force. The gravitational force came before this deduction, and the law of gravity was given by Newton. In 1755, soon out after Thomas Wright's speculation, Kant proposed that the galaxy name with capital G is actually one more name of our own galaxy. Uh, so Kant proposed that the galaxy must be a stellar disk, and there is no special place for solar system, and the other nebulas, or the other, by nebulas at that time they mean the faint diffused emission from coming from the sky, are actually island universe like our own galaxy. That means these are other galaxies present out there. And soon after that, it was William and Caroline Herschel. They gave a model for the galaxy, and they actually observed the stars and mapped the stars to give the first shape of a galaxy. And they gave the shape of the elliptical system to our own galaxy, with sun lying near the center of a roughly flat elliptical system, with the disk, or the disk portion or the plane of the ellipse to be approximately 5 times wider than the thickness of the ellipse. So basic, the semi-major and semi-minor axis of the elliptical shape that they deduced was approximately 5 times. Semi-major axis was 5 times the semi-minor axis. And then came the famous Captain Universe in 1920. He deduced that the galaxy, our own galaxy, is actually a flattened spheroid with decreasing stellar density of the distance from the sun. And the sun was approximately at 38 parsec from north galactic plane in his picture, and 650 parsec away from the center of the spheroid. So he essentially assumed that the uh, galaxy is spheroidal in shape, and the sun being the center of the system. Then Shapley proposed his universe, and it was based on the catalog of globular clusters. He observed approximately 95 globular clusters, and those globular clusters were around the center. The observation was showed that they are around the center of our own galaxy, and from there he deduced that we are in a flat disk kind of structure with diameter approximately 70 kiloparsec, and sun being far away from the center, and he deduced the distance of the sun from the center of the galaxy to be around 16 kiloparsecs. These numbers were far away from the present numbers of approximately 30 kiloparsec to be the diameter of the disk of our own galaxy, and 8 kiloparsec approximately to be the distance from the center. However, these guys did not take into account the absorption of light due to the interstellar dust. So in 1930, Robert Julius actually took into the account of the observation the effect of the light absorption due to interstellar dust and of the light coming from the open clusters or the globular clusters, and hence the present picture of Milky Way emerged. We'll come to a present picture a little later on in the discussion, but before that, I would like to point out at a very famous uh, Shapley Curtis debate, that is also called the Great Debate. And this was the debate to settle the shape and the size of the galaxy, of our own galaxy, and the size of the universe essentially from the observed sources known at that time. So on April 26, 1920, at National Academy of Sciences in Washington, D.C., there was a debate between H. Shapley, who was then working at Mount Wilson Observatory, and Herbert Curtis was working at Lick Observatory. Both of them gave two major pointers from there, that Chapelet was actually vouching for the fact that the nebulas that are there, which are basically the diffused emission that is coming from the sky, are actually part of the Milky Way. By nebula, by then they mean the galaxies like M31, which are not, right now very much in picture that these are extragalactic sources, are the galaxies. But he actually advocated the fact that these nebulas are actually the part of our own galaxy. And Curtis advocated, coming from the fact, giving the argument about the Doppler shift and the rotation and the dust lanes that were seen in the sources, nebula sources. He advocated that these are actually extragalactic sources, and you can find the details of the debate in this article that I've mentioned over here. So later on, around 3 years away from the debate, Hubble in 1923 he detected the Cepheid variable stars in M31, computed the distance of those stars in M31 galaxy. M31 is the Andromeda galaxy, which is our nearest neighbor, and estimated the distance of those galaxy to be around 285 kiloparsec, which is far away from the modern estimate of 770 kiloparsec. But it was enough to settle down the debate of these sources being extragalactic, and hence it was at that time finalized that okay, these nebulas are actually extragalactic sources and not the galactic one. And the Milky Way is just one of the galaxies, with sun not at the center of its galaxy. So both these guys agreed on the fact that Milky Way is a disk galaxy with sun not at the center of the galaxy. However, the distance estimate of the sun from the center of our own galaxy changed from that time. So that's the modern picture of where we are. So this is our planet Earth. It's a part of a solar system with sun at the one of the locuses and all the planets revolving around the sun in elliptical orbits. And then this solar system is further a part of the galaxy, and we lie along one of the spiral arm of the galaxy. We'll come to the spiral structure of the galaxies in a while. And we are approximately 8 kiloparsec from the center of the galaxy. And then came from here all these galaxies on the right. This is the deep survey image of Hubble Space Telescope, showing thousands of galaxies. Each dot over here in this image represents a galaxy, and so we are actually a very tiny part of the whole universe, coming ranging from the scale of uh, astronomical units, or a parsec, which is the distance of near a star, and to the scale of megaparsecs and higher. If you see the distance scales involved in the in case of the deep survey image of HST as shown in the right panel. So now coming to the classification of the galaxy, which Hubble gave in 1930. So he based his classification on the fact that the shape of the galaxies differ. So besides our own galaxies, there are as many as billions of galaxies that have been seen right now, and we are still counting the number of galaxies. Uh, and there could be as many as 100 million galaxies in our own universe. And the galaxies can be of different shapes and size, and broadly depending upon their shape, there are largely three classification of the galaxies: spiral galaxies, elliptical galaxies. Spiral galaxies are essentially disk galaxies with arms like spiraling like this. Elliptical galaxies are 3D ellipsoids, and irregular galaxies are the galaxies which has no particular shape to the galaxy. And Depending upon their shapes and sizes, there were two major classification, that is elliptical and spirals, for which the shape was certain, and these two can be characteristic, have their characteristic elements also present in them. So ellipticals have less gas content. They are relatively older, as if you see the if stars that are present in the galaxy, they are more evolved, and the stars are orbiting the common center of gravity in random directions. The spiral galaxies, on the other hand, are gas rich with young stars present in them, along with the central bulge generally containing some older stars. So there's a central bulge, as you see in the previous picture also, there's a central bright dot in this image. So you have which normally contained old stars, and the stars in spiral galaxies are orbiting the center of mass in almost circular orbits. So for example, in M31, the orbital velocity of the stars in the spiral M31 galaxy is around 200 kilometers per second. So, based on the shape, Hubble actually gave the famous Hubble tuning fork diagram, which resembles a tuning fork, and the this arm of the diagram contains elliptical galaxies, where the names go from E0 to E7, where 0 to 7 are the numbers, which essentially gives how flattened your ellipsoid is. So E0 is actually almost a circular or a spheroidal shape, and E7 is a elongated ellipsoid that we have. Then we come to lenticulars, which are neither spirals nor ellipticals, and they are termed as S0. From there are two branches of spiral. The one is an SABC, which are normal spiral with a small bulge at the center, and then spiral arm coming out of the bulge. And on the other hand, we have barred spirals, in which you have a small bar at the center of the galaxy, and then you have spiral arms coming out of it. These number A, B, C in small represent actually the winding of the spiral arms, as you see over here. If the picture is very clear, if you see the below one, SBA, the arms that you see are very tightly wounded, whereas SB opens up a little bit and SPC opens up more. So this ABC gives the winding of the spiral arm, how tightly wound your spiral arms are. Other than this, you have irregular or peculiar galaxies which do not resemble any one of these shapes, either elliptical or spiral. However, sometimes it's also said that they are in the intermediate stage, and their shapes have been disrupted by some recent interaction that is happening. So these are categorized differently. So this is a very clear diagram of the Hubble classification of the galaxies depending upon its shape. However, if we go on adding the galaxies to this beautiful simplified classification, the picture is something like this. So it's a zoo of shapes that are available to us, and these are ellipticals. Then you have further branching of ellipticals. These are irregular galaxies of different shape. Then spiral, they branch into spiral, and they here the galaxies have a strong bulge. Here the galaxies have a weak bulge. These are intermediate portions where the bar and the bulge kind of merge into each other. So the classification is though very simplified, but it still holds for many systems right now. But it's always not possible to actually distinguish between the galaxies based on these just by looking at them from naked eye or by measuring their shapes. But this is by far the most accepted classification of galaxies that we have. Now, coming back to Milky Way, if you look at the shape of the Milky Way, these are the schematics of the Milky Way. Milky Way closely resembles the type SBC in the Hubble's classification. And SBC, we mean that we have a small bar at the center of the galaxy, and you have a small bulge also there. and then there are spiral arms coming out of the uh, end of the bar. Right now, the most accepted picture here, the schematic shows only two arms coming out of the bars, but right now the most accepted picture of the galaxies that we have, it's a four arm spiral galaxy. This is the top view of the spiral Milky Way, and this is the side view of the Milky Way, where these dots on the above the disk plane and below the disk plane are the globular cluster. Sun is somewhere here at a distance of approximately 8 kiloparsec, and you have a dark matter halo on the top of it. This is the image of Milky Way. These are the images of Milky Way at different wavelengths from basically a side on view. And the topmost is the radio continuum image at 408 megaparsec. The next is atomic hydrogen. Next is a radio continuum at 2.5 gigahertz. Molecular hydrogen, infrared, mid infrared, and near infrared. Then this is the last third is the optical portion. Then the last second is X-ray, and the last one is gamma. Is the image of the galaxy in gamma ray. So basically, you see little different structure depending upon which wavelength you are in, and that wavelength gives us that what is the major component of the galaxy that we are observing. So, for example, in optical, if you see there's a dark patch that you can see in the center of the disk, which is basically the dust lane that you can. The dust lane is actually obscuring the light that is coming from in the optical wavelength. So the shape and the features that you see actually depend upon in which wavelength you're seeing. By that we mean what are we actually looking at. So molecular hydrogen, you will see something different. Radio continuum, you see something different. Atomic hydrogen, you see something. The structure and the details of what we see do differ, but largely it is well established that it's a disk galaxy with bulge at the center and uh, globular clusters over and above on the disk. So from here, we will move on to the discussion of how galaxies are formed. So one of the greatest challenges that was faced by the astronomers and that the astronomers are facing till now also is the understanding of how galaxies are formed. So observations show that the first galaxies actually took shape a little after the Big Bang. So the Big Bang is approximately 13 to 14 billion years. Right now, the present estimate is around 13.8 billion years old. And the oldest galaxies that we know as of now are approximately formed at 380 million years after the Big Bang happened. So they are approximately 13.4 billion years old as of now. So from there, we move on to two leading theories of how the first galaxies were formed. The first one says that the galaxies were born from very vast clouds of gas and dust when they collapsed due to their own gravitational pull. And once they start collapsing, the temperature and the densities of the region actually increased sufficiently such that the stars could form, and you get the whole galaxy in one collapse. That was the idea of the first theory. The second one says that, which is by far much more accepted, says that the young universe, actually the early universe, consisted of small lumps of matter, and those small lumps of matter keep on evolving, and some those gas clouds also had some star formation, and then those clumps of matter start colliding with each other to actually form the present galaxies that we have. So it was not a one huge bulk. I mean, in layman's language, it was not one huge bulk that formed at a given time. However, you had small lumps of portion that formed, and then they combined together. They were attracted towards each other. They collapsed into each other and formed the present picture of galaxies that we see now.
Mamta,
Yeah.
Some of the viewers are finding it difficult to read the text. In this one, is it
Uh,
possible for us to go full screen, or do we have to change the presentation? If you have to change, then
okay.
we'll keep it as it is.
Full screen mode.
Is it possible in this? Because we had a little trouble in this mode, right? To put it full screen earlier. What
Uh,
I will do is keep just the presentation. If it is difficult, then go ahead. Let's not spend time on this.
I will
So
just
go
try
ahead.
to. I will just
Ha,
try
ha,
to
ha.
remove the
Sure,
side
sure.
panel. Just give me a
Yeah,
second.
yeah. Yes, yes, yes.
I'll just try to
Yes,
increase
yes.
this.
And
Is
also, yeah, yeah, yeah. Yeah. Okay, that is one thing which has
is
happened.
that better?
Hopefully, that is better. Participants, please go ahead. Sorry, I interrupted in between. Please go ahead.
Yeah, it's perfect. So I hope the speed is okay. Okay.
Yes,
I'll
please go ahead.
continue from here. So that's these are the two distinguished models that we have, and from there, uh, this theory gave rise to the deduction that most of the early large galaxies were spirals actually, and but over the time, many of the spirals actually merged to form elliptical galaxies. This was one of the outcomes of the second theory that we had. So, what happened is one bit of evidence in support of this merger theory for the formation of large elliptical galaxies is that mostly the large elliptical galaxies that we see are there in the dense environment. For example, the centers of the clusters, large galaxy clusters that we see are mostly large elliptical galaxies, and these large elliptical galaxies are found in dense cluster environments and where the mergers are actually more common if you look at. So our own Milky Way, for example, will bump into Andromeda very soon, but the soon in astronomical scales is around 5 billion years from now. So, how the spiral galaxies are formed is the next question. So, ellipticals are formed from spirals, but how these spirals are formed is what we will now try to answer. So, the formation of spiral is a very complex process because of the components that are there in spiral galaxy. For example, if I go back to the schematic of the spiral galaxy Milky Way that we had, so we have a bulge at the center, which is a spheroidal bulge. Then you have a bar, then you have a disk galaxy, and the components or the composition of all these parts of the galaxies is different. For example, in case of bulge, this bulge is formed with old stars, is the old stars are found in bulge. Rather, I would put it that way, that observation suggests that bulge contains old star, and the disk of the galaxy is largely young stars, or the newly born stars are seen in the disk of the galaxy. Disk has more gas content, bulge the gas content is less. If the gas content is less, the star formation activity will be less in the bulge. So what happened is the following, that the formation of spiral is actually a complex process because you have different parts to the spiral that are formed at different times and possibly through different mechanisms also. So the bulge and the halo of the spiral galaxies are composed, that I've already explained, they are mostly composed of all old stars. This also indicates that the bulge and the halo of the spiral galaxy would have formed first, and this was formed from the primordial collapse of the individual galaxies or the gas clouds in early universe. And then the spiral disk, the disk of the galaxy, which contains mostly the younger stars, would have collapsed into the bulge later on to form the disk of the galaxy, and this is then thought to be found after the primordial collapse event. Primordial means the early universe evolution of history, evolution history. So this was a rough idea of how the collapse would have happened. So you generally have a gas cloud which collapsed to form the bulge and the halo at the center first, and then the disk component formed due to the merger or due to the collapse of smaller clouds in the vicinity of that bulge. So that is how the spirals are thought to be formed or are actually seen to be formed in the numerical simulations. So these are a few examples of spiral galaxies that you see. These two are grand design spiral. By grand design spiral, let's see the image on the right, which is much clearer. You have a very clear bulge at the center, and then you have two armed spiral, which is a grand design spiral. I've chosen this image. It's as we can see that there's a small galaxy on the right that has actually started merging into this galaxy. So there's a recent merger event that is happening into it, and this is M51 galaxy. On the right, it's M100 galaxy. M stands for the Messier catalog. There are around 5 6 catalogs that are there. For example, NGC catalog. There's also an SDSS catalog, the Messier catalog. So these are catalogs of galaxies. So M stands for Messier. 100 stands for the galaxy. That's the galaxy ID that you can call it. So there are around thousands of galaxies that are listed in the catalog, and each galaxy is given a unique ID number in these catalogs. Um, and Next is intermediate spiral structures. So you in intermediate spiral structures, you see spiral arms, but as you see in the right image, you have spiral arms like this, and then there are some other spiral arms that are emerging from here. There's one spiral arm over here which is coming out in between, not from the center bulge. And similarly, on the image on in the image in the right hand side, this is M101 and M33 that you see. And these are also the flocculant spirals. Flocculant spiral means you have a spiral and then you have a flocculant structure like threads coming out of the spirals. And this is a barred spiral. So you have a bar and then a grand design spiral coming out of it. So from here, let me just go back to this image. This is a very clear image in which you can see various stuff. So you also see the dust lane over here. Then you see this red portion also, which are the star clusters that are forming. And then you see white light, which is the light of the gas, and young stars are also getting formed over there. So these are a few tracers of spiral arm. As you see that they have a different position in the spiral arm. So, for example, the dust lane is like this. Then you have a red dot structure, which is the gas clouds where the star formation is happening, and then you have a gas arm also. So, these different structures actually give us an idea how these spiral arms are formed in a disk. So, see, it's a very hard coincidence that you see all these spiral structures, and they were formed while the galaxy was the gas clouds were merging into each other. So there has to be a physical phenomena that gave rise to these spiral structures. So there are a few tracers of spiral arms that I started talking about just now. So the star formation rate is much higher in the spiral arms as compared to the rest of the disk. We'll come to it why. There are mass arms which coincide with the maximum infrared surface brightness of the disk. Then you have gas arms which contains the maximum gas density in the disk. Then there are also bright star arms which have the maximum luminosity or density, and there are young stars present in this bright stellar arm. And there are other parts to the spiral arm. For example, there are dust lanes that you just now saw in the image. There is an arm corresponding to relativistic electrons, which traces the magnetic fields in the spiral galaxies. We'll not touch the topic of magnetic fields, but you have an ionized plasma present out there in the universe. So there is magnetic field also present there. The next tracer is molecular gas. For example, you have carbon monoxide molecules present in the galaxy, which traces the high density gas environment in the galaxies. Then you have neutron hydrogen arms, which coincide with the bright stellar arms also. And they are also useful in making the mean gas velocity maps, and hence probes the dynamics also of the spiral structures. And then you have H2 regions, which traces the star arms, stellar arms in the gas disk. I'll take a break from spiral arms over here and would like to point out one thing, that this neutral atomic hydrogen, actually the observation and the velocity that is coming from the neutral hydrogen actually deduced the presence of bar at the center of our own spiral Milky Way. So what happened was that in around 1970s, there was the observation of the radio observation of H1 line, which is the neutral hydrogen line, actually started. So, in that, the first observation was taken by Shane in 1971, to be precise, and he observed that the velocity of the H1 region, if you look towards the center of the galaxy, is far from circular orbits. So, then later on, uh, when this was observed earlier, and Shane in 1971 actually proposed that the observed velocity of the gas could actually be explained by a presence of bar at the center, which is pointing at approximately 20 degrees away from the direction of the galactic center. So that is how a presence of bar was deduced in literature, and this is approximately around 1970 that it was deduced, so it's not very old. And now let's continue with the spiral arm formations. So these are a few definitions that I'll use in the due discussion. The first one is the number of spiral arms. So as we saw in the previous image, the number of spiral arms present in the galaxies differ from various galaxies to very other ones. So in the grand design, you mostly see two spiral arms. In intermediate, you see, for example, here you see around 3 to 4 spiral arms. Here also you see two coming from the center and one emerging from in betweens. So our own galaxy Milky Way has 4 spiral arms, out of which 3 are emerging from the center bar, and the fourth one comes from in between. That is what is observed. And this barred galaxy also has 2 spiral arms. These flocculent, you can't make out the number of spiral arms, but there are certainly more than 2 present here. So the number of spiral arms actually differ from the galaxy to galaxy. And then you have a definition of leading and trailing spiral arms. So if your galaxy is rotating in one direction like this, and if this, I don't know if the picture is very clear or not, but this circular portion over here with an arrow pointing towards the left, my left, actually gives the direction of rotation. So if the tail of the spiral arm coincides with the direction of rotation, then you call it a leading spiral arm. And if it is opposite to the direction of rotation, then we call it a trailing spiral arm. So let's go to one of the figures to make it much more clear. So if you have this as the galaxy and the galaxy is rotating anti-clockwise, this is a trailing spiral arm, because if it is anti-clockwise, the tail of the spiral arm is actually in the clockwise direction. So it's a trailing spiral galaxy. If I look at this one over here, it's a, if your rotation is anti-clockwise, this is a leading spiral arm galaxy. The one on which is NGC 1300, which is a barred spiral, as you can see in this image over here. So this is about the definition of leading and trailing. Then you have a pitch angle definition of the spiral arm. So pitch angle, by pitch angle we mean the angle. So you have a disk galaxy, you draw a circle at some radius r in the disk. So the angle between the tangent to the arm and tangent to the circle at a radius r, at a given radius r, is actually the pitch angle of the spiral arm, and it's actually defined in terms of phi, which is the angular component r theta phi. Spherical, if you talk about in the spherical polar coordinates, phi is the angular coordinate. So it's just given by chord of alpha is mod of r del phi by del r. And then we have pattern speed. which is the angular speed of the rotation of spiral arms as viewed from an inertial frame. So you go to the frame of inertial frame of the galaxy rotation. Over and above the rotation, the speed with which your spiral pattern is moving is actually the pattern speed of the spiral arms. Okay, so from here, let's move to the formation of spiral arms. So, to begin with, the first thought was that spiral arms are actually rigid mass concentrations, and the galaxy must be rotating as a whole around its center with the angular speed equal to its pattern speed. But later on, it was observed that the spiral patterns move at a different velocity, angular velocity, as compared to the angular velocity of the or the rotational velocity of the disk of the spiral. So this picture was actually ruled out in very early in literature. So this is the first picture that we have of how the spiral arms are. So that's a very simple solid structure spiral arm moving along with the disk all the time. But this kind of structure is, of course, very difficult to form theoretically because different galaxies have different pitch angles, different number of arms, and all that stuff. So this also gave rise to the process that it's very difficult to actually sustain these kind of structures, to actually form these kind of structures to begin with and then sustain them. So the next theory that came into picture was that spiral arms are actually radial disturbances. So you have a disk like this, you disturb the stellar orbits and along one radius, and then it was very well established that you have differential rotation in the disk. That means the inner portion of the disk is rotating. The angular velocity of the inner portion of the disk is faster as compared to the outer portion. So the spiral arms will form after you have a sufficient rotation in the disk and you get the winding. But as you can see in this animation over here, that if that was the case, the arms would keep on spiraling and ultimately you have smoothened out the arms in the galaxy. So if you do the calculation of this winding that we can see over here mathematically, so if this dotted line in the diagram over here is your initial disturbance, and due to differential rotation your arm is formed like this in the galaxy, anti-clockwise is the rotation direction. Okay, so if spiral arms are material arms and the material in the arms is same and you just have differential rotation to form the spiral structure, so in the differentially rotating disk at any time t, if omega r is the angular velocity of the disk, then your due to the differential rotation at any position r, the phi of r and t will be given by some phi naught plus omega rt. That's the simplest approximation. So if I put this phi value over in the previous definition that we had for the spiral structures and put in the numbers for our own galaxy, for example, or Milky and this is Andromeda's numbers, for example. So for a flat rotation curve, that means you have a constant circular velocity of 200 kilometers per second at a radius of around 5 kiloparsec and the time of 10 giga years, which is the typical age of the galaxy of the universe. So the pitch angle, if you calculate, is approximately 0.14 degrees. However, if you look at the observation of the same galaxy, the pitch angle actually is 10 to 15 degrees. That means the angle that we calculated theoretically is much smaller as you see analytically. That means the winding is not happening. So theoretically, the winding is happening and the pitch angle will keep on decreasing. However, you see from the observation that the winding is not happening, and this discrepancy that you see in this kind of model is actually called the winding problem. That means the spiral arms are much more wound as compared to what we actually have. So the next portion that came was given by a Swedish astronomer, Bert Lindblad, and his lifespan was from 1927 to 65, and he during his lifetime actually struggled for how to find out how the spiral arms are formed. And he recognized that the spiral structures arise from the interaction between the orbits of the stars and the gravitational forces between the matter of the stars and the orbits in the stars. So he realized that, however, till his death, the people did many people did not the community did not believe him, and they were of the point of view that the spiral structures are actually formed by intergalactic magnetic field. So if this was the case, then we cannot explain the presence of grand design spiral. We can do a very small calculation, and from the presence of magnetic field, for example, the typical magnetic field in the galaxy is of the order of micro Gauss. So if that is the case, if you have the magnetic field in a galaxy of the order of micro Gauss, and you calculate the magnetic force that will be generated due to it, and these spiral arms forming due to this magnetic force, the grand design spirals, that is the typical two-armed spiral, could not be explained very well. So moving on from there, in 1964, around the end of the life of Lindblad, Tumre actually proposed that the spiral structures are formed by material clumping. So he said that there is a material clumping that is happening. Then you have differential rotation, which kind of destroys the clumping. And then there is regeneration of the clumping due to gravitational instabilities in the disk. So he says that some disturbance is happening, then the disturbances are destroyed by the differential rotation, as we saw in the previous animation. And then there's because of the presence of instabilities or disturbances happen again, and you get to see the spiral structures. And different kind of spiral structures are actually different stages of this whole process. However, this again could not explain the formation of grand design spirals. So, how you see a lot of galaxies having these kind of grand design spiral, most of them actually follow that with some or the other variation. So, that was one drawback, one major setback to the theory given by Tumre. And then came the proposal that at the same time, around the end 1964-65, the Lin Shu, the famous astronomers Lin Shu, proposed that the spiral structures are actually density waves. So they proposed the density wave theory now. So what they said is that there is a wave that is generated. So you have a disk structure like this. There's a wave in the disk structure like this. So you kind of imagine like it's a cylinder, and along the radius there is a wave that is generated, and there's a wave of compression and rarefaction that is happening with along the surface density of the disk. And this wave propagates with a different velocity. Okay, and then you have differential rotation over and above it, which kind of rotates that waves to give us the spiral structures that we see. So his theory had also one more assumption there, that these are the stationary waves, that is that they do not change with time apart from overall rotation that is happening. So the present understanding after this is the following, that the first portion of the hypothesis that was given by Lin Shu is widely accepted, that okay, yes, they are the density waves of compression and rarefaction happening in the surface density of the disk. And but these waves are actually, these spiral patterns are actually far from being stationary. That was the second assumption of the hypothesis is not accepted. So this also had one more problem of anti-spiral theorem, which actually, if I go back, the let me just explain it over here only. The hypothesis given by Lin and Shu actually, the theoretical analysis of that actually gave that there's an equal probability of the presence of the leading arm and the trailing arm in the spiral galaxy. So which part of the arm, whether the leading arm will be picked up by the galaxy or the trailing arm will be picked up by the galaxy, is a chance. So is coming from chance, which actually may not be the case. There is actually a certain kind of proper physical phenomena going back into the picking up of whether the galaxy is a leading arm spiral galaxy or a trailing arm spiral galaxy, and that constituted the anti-spiral theorem. And so this is the present view of formation of spiral galaxy. So if you see, this is a density wave structure. You have a continuous compression and rarefaction. So you have a wave that is there in the disk, and over and above you have the disk which is rotating like this. So material in the arm keeps on changing. So as you see in the previous figures also of the grand design spirals that we had. So let's see from here. So this kind of actually supports this figure and other figures also. If you zoom in those figures, they kind of support this theory. So this is your dust lane present. These are your stars and these are your gas arms of the present gas. So this wave, the material is actually moving in the anti-clockwise direction. So the dust lane, the stars and the gas are in the same sequence. So by the time the wave is traveling like this, so you have a dust presence, then you have a star formed. So when the wave was here, it started forming, the star formation happened. By the time you see the first light from the stars, the wave has moved ahead, and then you see the wave, the compression in the gas ahead of the star portion, star forming regions in the galaxy. So this kind of supported the present picture of the galaxy spiral arm formation. I've not, in the present discussion, gone into the details of how these waves are formed, which in itself is actually a complete discussion. So I would like to end here my discussions, and the floor is open for questions now. Yeah.
Thank you so much for taking us spiraling in through these galaxies and their formations. So there are a good number of questions. I'll now just start with the last one, which is here. You are able to
Uh,
see the studio, right? So I can, if I flash the question, you are able to read it. We can put the presentation in whenever needed.
okay.
So that's Pritpal Sandhu asking, do we have different radial speed about equator and pole of spiral galaxy due to differential rotation concept?
So differential rotation, basically the angular velocity at the center and in the outskirts of the galaxy is different. So I could not very well understand what do you mean by the different speed at the equator and the pole. It's the center and the outskirts of the disk galaxy. The angular speed is different. If you calculate the circular velocity, it's approximately the same. For example, in Andromeda, if you see, the speed is around 200 kiloparsec. So that's why you have a flat rotation curve. That's what it is called. Okay, then we
Next,
have.
Mrs. Jana has this question: how to calculate the speed of rotation of spiral galaxies? Mention the parameters to calculate, and galaxy being in line of sight or otherwise.
Okay, so it's like this. So if you have a face-on galaxy like this, so you calculate the proper motion of the stars. If you have an edge-on galaxy, you have a component of cos theta coming into picture. So you actually measure. So it's the plane of the galaxy, and you measure the proper motion along the plane of the galaxy in the face-on projection. So that's how you measure the rotation velocity of the stars. So if you want to look at it, I can actually show you a picture of the rotation curves that is there. So you actually will plot as a function of radius from the center of the galaxy the velocity of the stars in the disk plane. Uh, uh, Ratnashri, it's
Yeah,
okay.
your
You can.
presentation is there. Yeah, you don't need the presentation now. Shall I
This
remove it?
basically is not it.
Okay. Okay. This probably did
I think
come in
I've
some of the
answered the
discussions.
question of Vishwajit
Uh,
Jana. So,
yeah.
if you have any other question, you can put up a follow
Yeah.
up question.
Yeah. I
So,
have
how
put
can
it uh,
how
in
can you
some.
say that it's rotating opposite? I never said that it's rotating opposite. All I said that is that you have a rotation in the anti-clockwise direction, and the tail of the spiral is pointing in the opposite direction.
I think he had put
That's
this
it.
question around
They're
the time when
rotating in
we
the
talked.
same direction.
I think he had put this question around the time
The
you're
engine,
talking of
if
the
the
trailing and leading edges. In that
exactly,
context, he had asked this about the
exactly.
trailing and the leading. Yeah, yeah.
It's that it's rotating in the same direction, only the end of the spiral arm, so it's like this. So okay, I don't seem to have a curve. It's like this. I can show it by a paper. So one, it's rotating like this. So this is your center, this is your arm, it's rotating like this. In the other part, it's rotating like this. But in both the cases, the rotation is anti-clockwise. I mean, I'm just showing an example. So the rotation is in the same direction. It's just the tail pointing in the direction of rotation or opposite the rotation. What is the physical phenomena behind the spiral galaxies? Physical phenomena, I don't understand what in what sense
Probably
you are
in the
asking.
formation maybe.
Yeah, so it's the same that your central bulge forms first, the halo forms first by the collapse of the gas clouds, and then you have the disk structure formed. And the disk mostly forms because of the presence of angular momentum also in the gas that is there in the galaxies. So there's a lot of complex process that is going on. I just highlighted the major steps to it. So there's angular momentum in the gas. So angular momentum does not allow you to form spheroidal structures. It only allows disk. Uh, that's the most stable configuration that you will get after the formation. These structures.
I see a number of.
And
I think this
then you
is.
have there are disturbances over and above it, so you get the wave kind of phenomena happening, and that gives rise to the spiral. So you have a disk structure, and on the over and above you have disturbances and waves that are present in the disk, which gives rise to the spiral structures.
Um, there is this one has just come in. I think your lifetimes of galaxies. How many galaxies in the universe?
Okay, how many galaxies is not very clear, but I had a recent estimate of the number of galaxies that are observed that was given in 2016. So the recent number that was given by a 3D modeling in 2016, and this was given by Christopher, and the number is around 2 trillion. 2 into 10 to the power 12 galaxies is the recent estimate that we have.
Okay, there is this question about parameters for classifying spirals.
So,
Uh,
how can we classify spiral galaxies? So, first, it depends upon the shape. So, elliptical galaxies and the spiral galaxies, the major distinction comes from the fact that the spiral galaxies will have uh, an elliptical shape, a bulge shape at the center, and disk after that, whereas the ellipticals one will have a ellipsoidal kind of structure. Plus the composition of the galaxies is quite different. So in case of elliptical galaxies, they are gas depleted old stars. In spiral galaxies, they are gas rich galaxies, and fresh new stars are formed in the disk, whereas the central bulge will have old stars only. So the composition also decides gives us an idea about what kind of galaxy we are looking at.
so this question, in some sense, has been discussed
So the
through
shape of the
your answering.
galaxies evolve with time, and which factor decide the shape of the galaxy and how will it be? Okay,
Yeah,
it's not.
to some extent,
Yes,
yeah, this has been discussed. Yeah, go ahead,
yes. So the
please.
galaxies are evolving with time. You do see merging galaxies. I also showed an example in which there's a small elliptical dwarf galaxies which is merging into an grand design spiral galaxies. So yeah, it's an evolving process. It's not one stable phenomena.
There was this question which I did answer saying there are liquid states present, but do you want to take this
while
up too?
while liquid state is okay. If you look at if you call liquid the liquid is there is even
It's
most
not
of
that
them
it
are
is totally
plasma to
absent.
create liquid. Why do we
Oh,
need some
sorry, sorry.
planets?
I'm
No,
so
you
sorry.
don't need planets to create liquids. It's just the atmospheric condition of the planet or how they are formed, that some of them are in gaseous state, they're not liquid. So the planets themselves, but the condensation of water molecules on the planets happens because of the atmospheric conditions that we are in. So it's mostly the gaseous state that we are in while we talk about the universe. to be more precise. Even the stars are in gaseous state, but they are highly compressed. So that's more about it. Solids
There was
are formed from like planet, the surface of the planet of the Earth. It's just the collision and the temperature and the favorable conditions that we have, like atmosphere, has given the solid surface to the planet Earth. So there it's a quite evolved process, but not much about the liquids that you're talking about.
There are two questions about Andromeda, so why don't I show both of them and maybe you could take up the
Yep.
discussion following that. This was a simple question about distance, and I thought Vishwajit Jana had followed that up with about the prediction of Andromeda merging with our galaxy, and he then asks what will happen to the planets in our solar system. And
So, see the prediction of merging the galaxies. Okay, first I'll answer the distance scale. So, the present estimate of the Andromeda galaxy is around 770 kiloparsec from our galaxy. Regarding the prediction of the merger, so depending this prediction is coming from the orbital studies of both these galaxies in the local group. So we have a local group of galaxies in which we have Magellanic Clouds, other dwarf galaxies, Andromeda galaxy, and our own galaxy forms a major component of the local group. So, coming from the orbits, calculation of the orbits of the galaxy around the cluster which we are part of, we get that we will be merging soon on astronomical scales. So, most likely by then, our own solar system is may not be in place actually, because that's also depending upon the age of the sun. So you don't know what will happen to your own solar system, because we have never seen a merger happening. We have seen a merger happening, but we don't know the local effects. So it's not going to happen in our lifetime. So don't worry about that so much. Yeah, that's the answer. I mean, joke, that was just on the funnier side of it, but yeah, we actually don't know about it yet. Why the star birth rate higher inside the spiral arms than the center of the galaxy? Okay, very good question. So the spiral star birth rate is higher. See, you need higher concentrations of gases to form stars. In spirals, you actually, the place where you have a compression, it's a compression and rarefaction wave happening. So where you have compression, the gas density automatically increases. So the probability of actually the star formation increases there. That's the reason for star formation there. We read about galactic clusters such as Virgo, Perseus, and their names such as and Lucania and Saraswati. Yeah, exactly. So we are a part of Virgo cluster. How the scientists established that there are so and so set of galaxies are there in the clusters. So basically, what is happening is that, like I talked about the local group, the galaxy itself is gravitationally bounded. The stars and the gas in the galaxies are gravitationally bounded with each other. And over and above it, you see a larger picture which are gravitationally bounded with each other. And you have a clusters of portions of gravitationally bounded structures, which are various clusters. So for example, you have Virgo cluster, you have Abel cluster. So these are also gravitationally bounded systems. These are the largest gravitationally bounded system. Apart from clusters, you see different clusters only. Okay, and these clusters are separated from each other by approximately a distance of megaparsec, and they are connected by small filaments. That is again going back to the formation history of coming from Big Bang. So they've started forming from one, but these are the larger
network issue. Uh, uh, some problem has come.
Am I audible?
Yeah, yeah. I don't know whether from my side network issue was there or
I can't,
I could also not
ma'am,
hear for some
Ratna Shri,
time.
I can't hear you.
Oh, all right. I'll flash the question then. There is this.
How do we name galaxies? It's like I talked about. I've not given the details of it, but there are different catalogs in which the galaxies are registered. The earlier galaxies like Andromeda and Akashganga, given name given to our own galaxies, are the names given in the history, but the present nomenclature actually depends upon which catalog you are talking about. For example, you have a catalog of Messier, we have NGC catalog, we have the SDSS catalog. These are all depending upon by which telescope mostly you observe those galaxies, and then they are each of the galaxies given a unique number. Like Andromeda is given a number M31 in the Messier catalog, and I don't remember, sorry, the NGC number for it, but let me just look at it if I have. So there are various catalogs based on which you get the numbers right now. So the ancient nomenclature is not very well valid now, so you can't remember the names of 10 to the power 12 objects like that. So it's the number that is given to the galaxies as of now.
There was a question by from Santosh Kumar Gowda about the distances between galaxies, and Niranjan has answered that it differs, but you would like to
Okay,
uh,
so yes, it
add to
differs. For
this.
example, the typical distance between the galaxies is of the order of megaparsec. Yeah, so
Uh,
our nearest is 770, as I mentioned earlier, 770 kiloparsec. So, of the order of megaparsec is the typical distance between the galaxies.
there have
But
been
it's
some questions. Sorry. Please go
yeah,
ahead.
but yeah, I just said that they're changing because it's an
There,
evolving system.
there were a couple of questions. Somebody wanting to know the difference between a galaxy and a black hole, and somebody wanting to know what a nebulae and so on. Maybe would you just talk about the different components and answer?
See, they're black holes. Let's talk about black holes. Black holes depend upon what kind of black holes we are talking about. Also depends upon their mass. So, for example, first of all, black holes are formed as an end state of a star, and those kind of black holes are called stellar black holes. And the how the black holes are the center of the galaxy, those are supermassive black holes. The most accepted theory is that they are formed by continuous collision and accretion of the mass from the surrounding at the center, but it's not very clear right now. You can't like pinpoint that okay, this is how they are formed. And other way the black holes are formed are also by merging of two uh, okay, the merger of black holes is not very well established right now, but that's also one of the theories. And then the nebulas. Earlier, the name nebula was given to diffuse emission that you see in the star in the sky. So, for example, the Andromeda galaxy, the first observation of Andromeda galaxy, that was also called, then that the name that was given to it was nebula, and or island universes. So now the structures in that galaxies are much more reliably resolved, and you can even see the center of M31 galaxy right now with the present telescopes that we have. And the nebula essentially is the name given to the diffuse emission essentially that you see in the sky. And you have a lot of star formation activities also happening in the nebulas.
I think I have uh, put all the questions. In case something is missed, please just type it again quickly before we end the broadcast. And thanks so much, Mamta, for
One,
giving us this detailed walkthrough and answering all the questions so patiently. And wonderful, all the questions which have come, all of you who have participated in it. There have been so many relevant questions. It was lovely. Okay, there is
yeah,
one question. Mm,
which
Proxima.
Proxima Centauri. Yes, it's
Proxima.
around
Uh,
3.26 parsec from our galaxy. It's
We call
about
it Proxima for that region, probably. Okay, so I think that ends the questions which have come from there. Okay, so Bisuji Jana wants to know how you can be contacted. Do you want to give your contact here, or maybe in the Astro Adda group? I was suggesting that you will share your presentation there, the PDF in Astro Adda
okay.
group. Bisuji Jana, I hope you are in the group. And so they want to know your contacts. So rather than putting it here online, maybe in the group it could be shared. Is that
Yeah, yeah,
okay?
sure.
Hmm.
Yeah, yeah, completely
And
fine.
also, Biswajana, otherwise, by any chance, if you're not in the group, write to Nehru Planetarium at Gmail and we'll give the contact. Okay.
Uh, Ratnashri, it's my contact details are also there on the web page of Thapar University. You can just search School of Mathematics, Thapar University. You will get the
Right,
contact details.
right.
Yeah,
Just type Mamta Gulati and TIET. Immediately, you will get that page, her
yeah.
page on the website.
I'm
Okay.
already. Yeah, Bishwajit, then you will get the details in the group. I'll share the presentation with you. I am not in the group, so I think you can share that.
Yeah, if you give it to me, or you could come into the. So if usually what happens is for the next week or so, sometimes if students have more questions or they want to do something, then I've been asking speakers to be in the group over the next week. So we will see
Yeah,
if questions come in. I will ask you to come in to the group, and
I'll
anyway,
join.
your presentation will be shared in the
I
group.
think you have shared the link of the group with us, so I think I can
I
join
will
the
do
group.
that. So I'll end the broadcast now. Thank you, Mamta, and thank you all of you.
Thank you so much, everybody. Really nice discussion, and I enjoyed a lot answering the questions as well. Okay,
Okay.
somebody wants to add it. Yeah.
Yeah, I think. All right, the number is given. I will add. All right. So I'll